We are talking about redox reactions. We learned how to identify oxidation states. If the oxidation state is increasing, that's oxidation. That means electrons are being lost. If it's a reduction, we have a decrease in oxidation state, a gain of electrons. So let's look at this example. Use oxidation states to identify the element that is oxidized and the element that is reduced in this redox reaction. So it's instructing us to identify the oxidation states. So what's the oxidation state for SN? 0. Remember, oxidation state is the same as the charge if it's an ion. And here we have nitric acid. So we've got our nonmetals, and so this is a Fe765 situation. So there's no fluorine, but there's hydrogen. And so hydrogen gets to be what it wants. It gets to choose. And it chooses the charge it would have if it was an ion. And then next is oxygen, and oxygen gets to choose next. And so it wants to be -2. And there's 3 of them. And then nitrogen has to be whatever's needed to make up the difference. All of the oxidation states here have to add up to the overall charge on this thing, which is 0. So we've got -6 and +1, and so the nitrogen must be +5. I'm going to get rid of those because they're going to mess things up later. So then we can move over to our products. Now, SNO2, this is an ionic compound, right? We've got a metal and a nonmetal. And so we can just look at the charges on the ions. So the oxide ion has a -2 charge. And what's the charge on the tin ion there? So how many oxides do I have? I have 2 of them. +4. +4. So that one's +4. Here we've got nonmetals again, Fe765. The oxygen is going to be -2. And there's 2 of them, so what's the nitrogen? +4. And then we've got water at the end, again, Fe765. Hydrogen gets to be +1, and the oxygen gets to be -2. So looking for the element that's oxidized, oxidation is when the oxidation state goes up, right? So we're looking for something whose oxidation state gets more positive. Well, let's check our first thing here, our first element. Tin is 0 here, and over here it's +4. So it goes from 0 to +4. Is that oxidation? Yes, it is. Whoops. So if there's oxidation, there's got to be reduction in there somewhere as well. What element goes from a higher oxidation state to a lower oxidation state? Nitrogen. Nitrogen goes from +5 to +4. So that's reduction. What about everybody else? If you go through and check them, they are all staying the same. Now, it is definitely possible to have 2 things being oxidized or 2 things being reduced. You can even have a situation where you have one element where some of them are being oxidized and some of them are being reduced. All kinds of crazy things are happening, but usually it's, in this class, it'll just be 1. So oxidation and reduction have to happen simultaneously. It's like a financial transaction. If I give you money, you take the money, right? We don't just grab money out of the air and, if I'm going to sell you if I'm going to buy something for you, I don't just throw the money on the ground, right? It goes between people. whether that's in your bank account or hand to hand. And so the electrons are like that as well. Okay, so all of that is okay. And then we introduce this, and I'll just apologize ahead of time. This is confusing. We have things that are being oxidized and reduced, and then we have oxidizing and reducing agents. The reducing agent is the thing that reduces the other thing. So the reducing agent gets oxidized, and the oxidizing agent gets reduced. Isn't that nice? But let's think about movie stars, right? So a movie star has an agent, and the agent's job is to get this person roles in movies, right? Does the agent star in the movie? No, he arranges for the movie star to star in the movie. So here, the reducing agent doesn't get reduced. It arranges for something else to be reduced. The oxidizing agent arranges for someone else to be oxidized. Okay, so they're just like backwards of each other. So in this example, we're supposed to identify if we have a redox reaction for each of these, and then if there is a redox reaction, they want us to identify the agents. I think the simplest thing is to go through and identify what's being oxidized and what's being reduced. And then you switch the words, and those are the agents. So there's different ways to recognize oxidation, reduction reactions. We mentioned some categories: combustion, metal, non-metal elements reacting, two non-metals reacting. Honestly, you're not going to remember those categories. But we can look at the reaction and see, are ions being formed? Are things changing charges? Are things changing oxidation states? So here we have two elements. Elements are always just zero oxidation state. In lithium chloride, are there ions? Is this an ionic compound? Yes, it is. Lithium is a metal. This is a metal and a nonmetal. So this is lithium chloride, right? Lithium ion and a chloride ion. So lithium went from 0 to +1. Is this a redox reaction? Yes. Yes, it is. So here, lithium was 0 and chlorine was 0. Actually, lithium 0, chlorine 0, and oxidation states lithium is +1 and chloride is -1. We can think of it in terms of oxidation states, or we can think of it in terms of oil rig. Oxidation is loss of electrons. So when lithium becomes a positive ion, it does that by losing an electron, right? Oxidation is loss of electrons. So lithium is being oxidized. Chlorine is being reduced. Yep. And here, there's not really many choices because there's only two elements, so chlorine has to be the other one. So lithium is being oxidized, and chlorine is being reduced. Okay? So that part, doable. And then you throw the agents in there and things get kind of weird. But if this is oxidized, it's not the oxidizing agent. It's the other one. It's the reducing agent. So that's being oxidized, it's the reducing agent. Chlorine is getting reduced, it's the oxidizing agent.
So they're opposite.
They're opposite. So at least there's that. It's just exactly backwards. Equation 2. Is this a redox reaction? Look what aluminum is doing.
The ions, it gain, so yeah.
Yeah, the charges are changing. So this is a redox reaction. And we have aluminum going from 0 to +3. So what's that? Oxidation. So this is being oxidized. And then the other reactant is SN2+. And that's being reduced. Now, where you can mess up in a multiple choice question on an exam is they could have aluminum, SN2+, Al3+, and SN. And sometimes students want to say, well, the SN is being reduced. No, the SN is what you have after the SN2+ is reduced. So when we're talking about what's being oxidized, what's being reduced, or what are the agents, we're always talking about the reactants and not the products, okay? So if aluminum is being oxidized, what kind of an agent is it? Reducing. Is a red agent. And then tin 2, because it's being reduced, must be an ox agent.
So the states don't help us at all? Like if, the state that they're in, state of matter? For
No.
example- Okay.
Solid, aqueous, that plays no part in this. Yeah. Oops. Okay, number 3. Is that a redox reaction? I didn't mean to draw a line through lithium chloride.
No, it's oxidation, it's just losing it,
Well, let's think about, well, there's a bunch of ions in this, right? What are they?
no? Lead.
We've got lead with what charge? 2+. And then there's nitrate. And then here we've got lithium plus and chloride. And here's chloride again. And so if we go through these, we see, oh, all the ions are staying the same. This is the 2 pairs of ions coming to the party in the beaker and mixing and mingling. They didn't get oxidized or reduced, they just swapped partners.
So we're just doing.
It's not a redox reaction. No electrons were transferred. Copper plus oxygen to make CO2. This is one where you have to use oxidation states because there aren't any charges. Well, again, our reactants are both elements, so their oxidation states are 0. And in CO2, we apply Fe765. There's no fluorine, there's no hydrogen, but there's oxygen. What does oxygen want? -2, right? So that list, Fe765, is who gets to choose first, and they're always going to choose the charge they would have as an ion. So oxygen as an ion becomes a 2- ion, so it's going to choose 2- or -2 as its oxidation state. So then what's the carbon? +4. So we have 2 reactants here. We have carbon and oxygen. Is carbon being oxidized or reduced?
Because it's gaining. Went from 0 to 4 plus 4.
But reduction is a reduction in the oxidation state.
Oh, okay, so oxidation.
What you meant was it's the reducing agent. Right? So carbon is being oxidized because its oxidation state is going up. That means it's the reducing agent. So then the oxygen going from 0 to -2, the oxidation state is being reduced. This is a reduction. And so then this is the oxidizing agent. And the reason it's called an oxidizing agent is because oxygen was the first thing that was observed to do this, and so then they realized that other things did it as well. Any questions? If we put a piece of magnesium metal into a beaker containing copper ions, a spontaneous chemical reaction will happen. It's a redox reaction. The copper ions will become copper atoms, and the magnesium atoms will become magnesium ions. And we'll see that the blue color of the solution disappears, and we get this weird looking stuff on top of the metal. This is very much like when we did experiment 2, where we put the zinc into our beaker with our blue copper solution. And there was a lot of fizzing and stuff, and the zinc disappeared, the blue color disappeared, but that reddish copper appeared in the bottom. Okay? What if we do the opposite and put a piece of copper into a beaker with magnesium ions? Nothing happens. Which, if you think about it, kind of makes sense, because that first reaction is kind of like a ball rolling down the hill, right? Well, if you start at the other end, is it going to roll back up? Things don't go just in one direction or the other direction because you're starting at that end, right? So the reverse reaction doesn't happen. So copper is not going to lose electrons to magnesium, but magnesium will lose electrons to copper. So there's nothing in the periodic table that shows us the order of this, but experiments have been done, and they've made a list. It's called the activity series of metals. It shows us which are the most active. So at the top, those metals have the highest tendency to lose electrons. And so what we do is we write 2 half reactions. So an oxidation and a reduction. And those together make one reaction. So if we look at this, we have 2 half reactions going on here. We have magnesium going to magnesium ion plus 2 electrons. And we have copper ion gaining 2 electrons and making copper metal. So oxidation is loss of electrons, magnesium is losing electrons. Reduction is gain of electrons, the copper ion is gaining electrons. When we put those 2 half reactions together, the electrons that were given off by one got picked up by the other, and so they don't show up in the balanced chemical equation. So this is the list, and I can tie this into the party in the beaker. So now these are high school kids going to this party, and the girls have made a list of the guys, right? And it's like, who's the most desirable, like captain of the football team or whatever. I don't know what's cool these days. But they've got this list of, this is the most desirable guy down to this guy nobody wants to be with, right? It's not nice, but we all know what happens, so let's just not pretend. So if we look at that reaction that we were just talking about, where we had magnesium going to magnesium ion, and we had copper, oops, I almost made that into an arrow, but I saved it. It's a plus. So the way we use this activity series is we're going to look at these guys. Now, maybe what we had here was maybe copper oxide. Well, it's probably not. Let's not do that. Let's do copper chloride. I think that's soluble. So what's a little different here, copper brought a date to the party, but magnesium came by himself. We used to call that going stag. Went alone instead. You didn't bring a date. I don't know what they call it these days. You can tell me later. So magnesium and is going alone, and copper's going with chloride. And at this party, they mix and mingle. And chloride is checking out the list because you got to keep that with you all the time, right? So here's magnesium, and here's copper. She came with copper, but magnesium's there, and he doesn't have a date. So what's going to happen? She's going to take him because he's more desirable. He has a greater tendency to lose electrons. Interpret that however you want. So chlorine's going to leave with magnesium, and copper's going to go home by himself. Sad. Well, a lot of times we'll just be seeing half reactions, or we won't see what what the anion is. We'll see net ionic reactions. So how do you look at that? So magnesium plus Cu2+, because what we need to be able to do is predict if this is going to happen or not. Is that a reaction that will happen? So now we've taken the girls out of it, but I know who has the girl to start with because he has a charge. He's charged up, he's excited because he has a date, right? He's going to the party with a girl. Magnesium is just all flat. It's like, eh. So they go to the party, and what this is predicting is that magnesium is going to leave charged up because he's got the girl, and copper's going to be flat, 0, because he goes home by himself. And so to predict whether that is spontaneous or not, whether that reaction will happen, we look at the list and see, well, is the girl going to like magnesium better than copper? Yes, the reaction will happen. Okay? You do not need to memorize this list. I don't remember the list. I'll look at it if I need it. Okay? Which metal is most easily oxidized? So here we have the elements, and in this reaction where they would get oxidized, they would end up with a charge at the end, meaning they're going to get the girl. So what we're looking for here, which is most easily oxidized, which one is highest on the list? So we go look at the list. Oh, sodium's right up there. So sodium's highest on the list, which means that if sodium shows up at this party and chromium or gold come with a date, they're going to lose her, right? So sodium is the most easily oxidized.
Could we also look at his electronegativity?
You really can't look at it in terms of electronegativity. Yeah, it's more complicated than that. It's just the list. Yeah. If there was a simpler way, we would tell you about it, honestly. Okay, so this is the kind of thing that you might have to do on a test, given an activity series. Determine whether each redox reaction is spontaneous, meaning does this reaction happen? So this is the last slide of the chapter. This one is zinc coming by himself and nickel's got the girl, right? And this is predicting that zinc's going to leave with the girl and nickel's going home alone. So what we need to ask ourselves, is zinc more desirable than nickel? So we go to the list and we look. There's zinc and there's nickel. Yes, zinc ranks above nickel, and so that one will be spontaneous. So this one, yes, spontaneous. What about if zinc goes and calcium's there with a girl? This is predicting that zinc is more attractive, more easily oxidized than calcium. Again, we just need to go and look at the list. There's zinc, and calcium's up here. So what this predicts is that calcium would take the girl from zinc. Definitely not going to happen the other way around. So we can write this equation, but it's not actually going to happen. That is not spontaneous. The reverse reaction is spontaneous. If calcium and zinc ion are at the party, oops, did that backwards. Yeah, that's not copper, that's calcium, it matters. Calcium's going to take the girl from zinc.
So like on an example, you basically like, let's say it's this two question, we have to figure out if there's spontaneous or not. And then would you want us to rewrite it like you just did?
No,
Oh,
no. It would just be, I mean, it could be a true-false question, or it could be choose the one that's not spontaneous.